Oh, did I get an extra one in there?
Yeah.
Margarita. All right, so homework 1 was working with 2's complement, and we talked about these on Thursday. Let me just make a couple of comments. First thing, make sure you show your work. Okay, now some of these were pretty easy to do in your head, but if you write down the answer and the answer is not perfectly right, and I don't have any work, I can't give you partial credit. And I usually give a lot of partial credit. So if I can see that you were doing the right thing, if I saw that you complemented your number, and then you added 1, but you messed up when you added 1, right? I'll give you most of the points for that usually. So make sure you show your work. And just to clarify, this came up last week also. We have this procedure where we complement and we add 1 to a number. Will people fall asleep if I keep the lights off? I'm going to keep the lights off because it's a whole lot easier to read, I think. We have this procedure where we complement and we add 1 to a number. You only want to do that if you're trying to convert a number to the negative of its current value. Okay? Not necessarily making it negative, less than 0, but if you're trying to convert a number to the negative of its current value, if you're trying to change its sign, the procedure is complement all the bits and then add 1. So for example, if we just do 4 bits, this is the number -1. If we complement and add 1, that will give us +1. Right? So complement, add 1, that's +1. If we complement that and add 1, that gives us the negative of this. So this is not how we can use this to convert a positive number to a negative number, but if we start with a negative number and we do this, we're going to end up with the positive version of that number. Okay? So this procedure, if I ask you to write -127, right, you can start with 127, complement add 1, that gives you -127. But if I asked you to write the number 3, you can write down, that's the number 3, don't complement it and add 1. Unless you're trying to get the representation for -3.
I just wanted a clarification.
Mhm.
So when you asked for a hex on the homework, did you still want 8 bits for those decimal points?
For homework 2?
Yes.
I mean for this latest homework?
Yeah.
So when I said write these in hex, so write 2 hex digits before and then a period and then 2 hex digits after. Yeah.
I actually have a question really see if
On the current homework?
Yeah.
All right, let me make one more comment on the old homework though. Use your full name on the homework, okay, and also on the labs. Try to avoid abbreviations, just to keep things totally clear. When you convert to hex, the easiest way to convert this 16-bit number to hex is just break it into groups of 4 starting from the right. So if we had an extra bit over here, we would put that by itself and put zeros on the beginning. Break it into groups of 4 and then write down the hex digit corresponding to each of those 4 bits. And so this 16-bit number is the same as B517 hex. You can also do this by converting this to decimal and then divide by powers of 16. It's the same result in the end, but that's a lot more work. Okay, one of the reasons we like using hex is because we don't have to convert to decimal first. We can just break into groups of 4 and write each digit for each group. But it's the same thing as finding powers of 16, because this is really B517. This is really 7. This is 1 times 16 to the first. This is 5 times 16 squared. And this is 11 times 16 cubed. but make your life easy when you can. All right, so questions on homework 2.
Yeah, we just do H, just the last one.
Converting to decimal.
Yeah, decimal and then hex.
So, were you able to convert any of those?
H?
What
Yeah,
is-
I was able to do 3.14. I just want to make sure I did the process correctly.
So 3.14?
Yeah.
Okay, so you want to write this in binary, right? So how do we convert a general number like this, something that's not an integer, to binary?
Start with 3. And
Start with the 3, and that's going to give us
0, 0, 0, 0, 1, 1. I think.
right? So 2 1s, that's 3, and we want 8 bits, so it's going to be 6 zeros and 2 1s, and then a period. And then and if we didn't know what 3 was, we could divide by 2 and take remainders, right? Do the thing we did in the earlier problems. So the 0.14, we have this algorithm where we repeatedly multiply by 2 and then take the fraction. So times 2 is 0.28. 0.28 times 2 is, and let me put my zeros in here, 0.56. And it might make some math errors. And as we're going through this, right, we're taking the thing to the right of the decimal point and copying that over here and multiplying by 2. And when we're done, it's these things to the left of the decimal point that give us our binary representation. And the first thing we get, that's the first number after the decimal point. So we're actually getting 0, 0, 1, 0, 0, 0, 1, 1. Hey, we got 8 digits. Good. All right, so they go in this order. Is that something like what you did?
I have
No.
a question.
Yes.
For the other ones, for the 0 point, whatever,
Mm-hmm.
do you do 0 point and then 7 places, or do you do just point and then 8 places?
I didn't really specify, but go ahead and do 8. If you did 7, I won't worry about it. But since these, yeah, I should have specified more precisely. But since we're really doing things that are, you know, just to the right of the decimal point, I would go ahead and do 8.
Is there an alternative way to find the 0.14?
Other than this? Yeah, there's a few different ways you could do it. You could do trial and error. So it's the same thing as doing trial and error on things bigger than 1. We know that this is the 0.5 place. This is 0.25, 0.125, 0.0625, 0.03125, and so on. And we're trying to write 0.14. Well, this is too big, so it's going to go in 0 times. This is too big, it'll go 0 times, but this fits. So it goes in once, and now you do 0.14 minus 0.125, and that leaves you with 0.015. And this is too big, and this is too big, and the next one will be too big, but the next one will go in. So you can trial and error it like that. But it's a little harder with things to the right of the decimal point because these get really big quickly.
So the multiplying is the fastest.
Multiplying is probably the fastest. And it always works, and it works for different bases too, not just binary. So if we got this answer, how would we write this in hex? What's 3 written as an 8-bit hex number? 0, 3. if we want to make it actually 8 bits. So there's 4 bits of zeros, there's 0, 0, 1, 1. And this thing over here, what would that look like in hex? 2, 3 hex. Right, 0, 0, 1, 0 is 2, 0, 0, 1, 1 is 3, perfect.
Would you write down as 0, 3.23?
Yeah, so the way I asked you to write it, I would probably do it like this. And you can put an X on there if you want. And I'm not being precious about like the format and the syntax and stuff like that. I really want to know that you can convert these things and get the ones and zeros right. All right, other questions on the homework? All right, go ahead and turn those in then, and I'll grade those up along with your labs. There's a stapler in the front desk out in the lobby area. Any other homeworks? All right. Awesome. All right, so what I want to do in the first half of class today is I want to continue this design process, starting from a description of a circuit and leading to an actual working circuit on a breadboard. Okay, things you'll be doing starting in lab 3. You don't actually implement your traffic light in lab 2, but you design it further. So there's this process of going from the description of the problem to a system diagram, truth table, and from the truth table, what we want to do next is go to a logic diagram and then a wiring diagram, and then actually implement it on physical hardware, and then test it and debug it. Okay, so the end of those steps, that's what I want to go through in this first half. And then after break, I want to talk about lab 2, okay, and talk you through the expectations for that. And then we're going to start expanding our understanding of Boolean logic and Boolean algebra, and how we can use some of the facts of Boolean algebra to simplify our life when we're designing and building circuits. Okay, so that's our basic plan for today. So I'm going to stick with the example we were using last time, which was this combination lock. Okay, so we got a combination lock, and it's going to have, we'll stick with 3 inputs. We'll call them A, B, and C, and 1 output X. And A, B, and C will be equal to 1 if our button is pressed, and 0 if released. And X, 1 will be unlock, and 0 will be locked. So our goal is to build a circuit that takes 3 inputs, 1s and 0s, and generates this output X, which is a logic 1 or a 0. And it's understood somehow that 1 means 5 volts and 0 means ground, or 0 volts. But that's got to be specified somewhere, so the customer's told you this. So we don't know what kind of buttons are going to be hooked up to A, B, and C. We don't know what the locking mechanism is. Is it a solenoid that's, pulled by a magnet? Is it something futuristic? We don't know. We don't care, right? We see the problem as this. All we got to do is design something that takes in 3 signals, which are at logic level 1 or 0, and generates an output signal at logic level 1 or 0. And the person who's taking this and hooking it up to their car, they deal with, okay, how do I arrange that when you push this button it generates a logic 1? Okay, but they're not worried about what goes on inside this box. So this is our job, is to design this box. And we said we go from a description to a truth table. And here's a typical truth table for 3 inputs. So it lists all the possible combinations of those 3 inputs, A, B, and C. And for each combination, we just list what the value of X should be. Okay, so we'll put a secret note here. We'll put it in purple because it's secret. And our unlock code was 101. So when the input is 101, we want the output to be 1, that says unlock. And in any other case, we want the output to be 0. So that was the truth table we came up with. And then we added a wrinkle, which said we wanted a second unlock code 010. So we change our truth table and we say, okay, there's another unlock state. At this point, you can hand this truth table to any digital engineer, someone who's completed 250, and they can build you a circuit. They might use AND gates, they might use XOR gates, they might use magic dust, who knows. But they can give you something that will respond to 3 digital inputs with this output. Okay, so we talked about one way to do this. We'll talk about different ways to do it on Thursday. But one way to build a circuit for this is to write an equation for X using ands, ors, nots. And the idea was, look at every row where we want X to be a 1. And we're going to write a little piece of an equation for each of those rows. So for this row, we're going to say, well, we know that we're in this row if A is 0 and B is 1 and C is 0. And saying that A is 0 is the same thing as saying A bar, not A, is 1. So if A bar is 1 and B is 1 and C bar is 1, then we know that this is what the inputs were and we want our output to be a 1. On the other hand, if A is a 1 and B bar is a 1 and C is a 1, then we're in this row and we also want the output to be a 1. And we want the output to be 1 if this is true or this is true, so we OR them together. And so this turns out to be a perfectly good equation for this truth table. Put this in parentheses since my bar got a little sloppy. Yes?
Do you have a preference over bar or the dash behind it?
I like bars. The dashes can be a little confusing whether they go in front or behind. That's the only problem. But if you throw it in parentheses, that makes it a little clearer. But if you're writing these by hand, and I encourage you to write these things by hand because it'll make life quicker, put a line on top. All right, so here's an equation that represents this truth table. If we can build a circuit that implements this equation, we've got our circuit. So let's do that. All right, so there's our equation. Well, we know how to invert things. We can put them through an inverter, right? So we haven't talked about hardware yet in here officially, have we? But from 120, right, you've worked with these things, these integrated circuits. So they're these little packages. They have a bunch of legs on the bottom, and they fit into protoboards. So you map the connectivity of the protoboard in lab 1, right, which refreshes your memory that everything along these vertical lines are connected. So these 5 holes are connected together. These 5 holes are connected together. But these holes and these holes are not connected. Okay, there's a break along this middle line. And these holes and the row of holes next to them are also not connected to each other. So if you want to use this to build a circuit, right, you can take your chip and you can put it into anywhere on the board as long as it straddles that middle line. And what we've done now is that this pin is connected to all of these holes and nothing else. It's not connected to the other side because there's a break in the middle, and it's not connected to pin 2 or pin 3. And so if we want to make a connection to that pin, we can take a wire and we can put it in here, or here, or here, or here. Okay, everybody remember this? All right, so we can wire up our circuits using this approach. So remember, if you look at your chips from the top, they look like this. There's a little notch on one side, and there's some writing that'll tell you a bunch of information. And it's usually pretty faded if these are old chips. But when you look from the top and you put the notch right there, this is pin 1. And you go around counterclockwise. So this would be pin 1, 2, 3, 4, 5, 6, 7. If it's a 14-pin chip, and 14 would be in the upper left. Okay, why does that matter? Because to use these devices, you need to know what the pins do. And so on the engrcs.com website for this course, there's a section labeled components. In fact, let's just go there. Just go to linuxengrcs.com and look under resources and component specifications. And here's the data sheets for all the different types of chips that you're going to use in this class. So let's look at a 74LS04. And it's called a hex inverter. So an inverter does this NOT operation, right? If you put in a 0, you get out a 1. If you put in a 1, you get out a 0. It's a hex inverter because there's 6 separate inverters inside this one chip. Okay, this is pretty miraculous, right? 6 inverters. If you go way back and you look at these things, these were big boxes to implement these because they were built out of vacuum tubes. Okay, so these things are awesome. So there's a shortcut guide to this. So top view, they're showing you the pin numbers. Ground is ground, VCC is power. Okay, that's just a symbology we'll get used to in here. VCC means power. Ground is sometimes called VSS, but usually it's just GND. And we're looking at a 74 LS04, so it's this diagram. If we had a 5404, different pin numbers, right? Ground is over here. Okay, and our pins are labeled 1A, 1Y, 2A, 2Y, 3A, 3Y. What does that mean? Come down here and you'll see the function table, truth table. Basically, on the input is A, the output is Y. If the input's high, the output's low. If the input's low, the output's high. That's your inverter. And here's a logic diagram. Come in on pin 1A, and the output is inverted on pin 1Y. 2A, 2Y, and that's a symbol for an inverter, right? We talked about these symbols the other day. Okay. And there's a logic diagram for what this thing does. It takes A, complements it, sends that to Y. So everything you need to know about this chip is available in the data sheet, along with lots of things you don't need to know. So here's the information you need for ordering it, because there's lots of different types of 74 LS04s, right? And you can get them in a tube, big long plastic thing. You can get them stuck onto a piece of tape and rolled up in a reel. And they don't look like this. They're usually really small and flat. But that's something you can plop into a machine that's going to build circuit boards for you. And it's easier for that to just pull them off a reel like this. You can get them to operate at different temperature ranges, 0 to 70, minus 55 to 125, and so on. And here's what's going on inside. So in our 74 LS04, this is the circuit that's being used to make one of these inverters. And there's 6 of these inside this chip. Okay, so it's got resistors, you use those in 120. It's got transistors, that's what this thing is. It's got something called Schottky diodes, that's what these symbols are. They're kind of like LEDs. And your input goes there, your output comes here. It's just a 120 circuit with transistors and diodes. But I mean, it's an analog circuit. There's nothing magic about it that makes it digital. But the way this circuit's designed, the output is usually either 5 volts or 0 volts. And as your input goes from 0, 0.1, 0.2, 0.3, 0.4, your output stays high until your input gets above about 2.5 volts, and then your output drops down to 0. So that's what's going on inside. This is the maximum values of things you can put in. These are the recommended operating conditions. And here's information about the switching characteristics, because this is a physical device. If you put a 0 in, you get 5 volts on the output. If you set the input to 5 volts, the output doesn't immediately respond. It takes a little while. How long does it take? Roughly 8 to 12 nanoseconds. Okay, if you're going from a low to a high, it takes 12. If you're going from a high to a low, it takes 8. But it could take as much as 22 nanoseconds. Okay, that's the maximum. And there's more recommended conditions and all kinds of information in here. There's ways that you can build test circuits for it. And then important notices, which tell you, like, they assume no liability for how you might use this chip. And they usually tell you not to use it in nuclear or life-critical applications and things like that. So everything you want to know about this is in this data sheet. And every device that you're going to use in here has a data sheet. And they should all be available through that engrcs.com website. All right, so back to our circuit. We know how to make an inverter. We just use a 74 LS04, right? And we can draw an inverter just like this. So what do we want to do? We want to take A and we want to invert it. And we want to take C and invert it. And we want to take B and we want to put those into an AND gate. And then we also want to take A and we want to take B and put that through an inverter, and take C and put those into an AND gate. And then we want to OR those, and we get our output X. So that's not a bad first version of our circuit diagram. But A is on here twice right? And there's not really two A inputs. If you look at our system diagram, there's a single input A, B, and C. And this doesn't match because we got two A's, so let's do something like this. Let's just connect that over there. And let's take our C and connect that over here. And let's take our B and connect that over there. And I get circuits like this on homework all the time. Okay, it's not ideal, obviously. It's technically right, but if you hand this to somebody and say, hey, can you build this for me? They're probably going to say no. Okay, and if your circuit is more complex, this is a relatively simple equation after all. If your circuit's more complex, you can easily make a horrible looking rat's nest. Okay, so let's look at a way to implement this equation or any equation that makes it really easy to see what's going on. Okay, and I know some of you have done this before, so this may be a refresh. Okay, we have three inputs, A, B, and C. I'm going to write those across the top. And I'm going to run a line down from each of those. And near the top, I'm also going to break off a copy of that, and I'm going to invert it and run the inverted output vertically. So now I've got a bunch of lines where I can pull off A, B, C, as well as A bar, B bar, C bar. And here's the equation we're after again. All right, well, I want an AND gate that takes A, B bar, and C. Here's my AND gate. And I'm just going to connect to the three inputs that I want to feed into this gate. So I want one input to come from A. I want one input to come from B bar. I want the third input to come from C. And so this is A, B bar, C. And the other thing I need to generate is this second AND term, which should AND A bar, B, C. So I'll run one of its inputs to A bar, the second one to B, and the third to C bar. And so this output is A bar, B, C bar. And if I had other terms along here, I could just make more AND gates, and nothing's ever crossing over anything except these lines here, and I'm drawing these dots to show where I'm actually connecting. So there's no connection between this line and, say, this line. Right? The connections are only where the dots appear. And then once I've generated all of my AND terms, I can take those and run them into an OR gate, and there's my output X. And that hopefully looks like a more reasonable circuit to work with.
Are you gonna be looking for ground and stuff?
Not yet. Very soon. So this is what I'm going to call a logic diagram. It shows how we can take a bunch of logic gates, ANDs, ORs, inverters, and get an output from inputs. But we can't yet put this on a proto board. We don't have an A in our parts box that we can pop into our proto board and connect to the input of an inverter. Okay? We still need a way to generate these inputs, and we still need to do something with X. Now, if we were building this to give to a customer who asked us to implement this, this would be what we give them. Okay? And it would just have three spots here where they would connect their switches A, B, and C, and this would be where they connect their whatever is going to the output X. Okay, but for us, when we're doing labs, we're usually going to want to set the inputs to certain values and look at the values of the outputs. So we're going to use switches and LEDs. So this is our next topic. So we need to add switches and LEDs. Okay, so this is an LED. They don't stay well on paper. It's a light emitting diode. A diode is a device that allows current to flow in one direction but not in the other direction. It's a light emitting diode because when you run current through it, it lights up. Okay, so it's basically a fancy light bulb, but it's one that doesn't burn out, at least normally.
Even at high currents?
At high currents, it'll burn out. But in normal use, if you stay within the range, it doesn't burn out, whereas regular light bulbs do
Oh, they last
over
very long?
time. They what?
They last very long?
Yeah. Yeah. It's very rare for them to fail. All right, so the direction in which you hook these up is critical. Okay, so there's a few ways to find the direction. The way most people use is, if you look at these, the legs have different lengths. Okay, the shorter leg is ground. So shorter leg is ground. This is for an LED. And the way you hook this up, so here's our symbol for an LED. So one end is going to get connected to ground. And the other end goes to whatever is sending current through this. So if I were to take this LED and hook it up to this point in my circuit, whenever this OR gate outputs a logic 1 that's 5 volts, it would send current through here and my LED would light up. But it would probably blow up pretty quickly. Well, not blow up, but it'll burn out very quickly. It makes a little popping noise. It smells bad if you really get close to it. So when we use LEDs, we always need to put a resistor in series with them. And we typically use a 1 kilo ohm resistor. The reason is these things don't have resistance. So 120 flashback. So here's a 5 volt source, here's an LED. So this is 5 volts on this side, this is 0 volts on this side. If the resistance through here is 0, V equals IR, I equals V divided by R, which is 5 divided by 0, which is infinity. You get infinite current, theoretically, flowing through here. That's more than it can handle. It can only handle about 20 milliamps. So if we put a resistor in here, we have 5 volts over here, 0 volts here. I equals 5 over 1,000. That's 5 milliamps. That's nice and safe. So anytime you use an LED in a circuit, make sure you've got a 1 kilo ohm resistor in series. Now you can put it here or you could put it here. Makes no difference. But it's got to be somewhere in there. And if you don't, then there's a good chance you'll burn this out, and then when you hook it up correctly, it doesn't light up because it doesn't work anymore. So you got to toss it, get a new one. And they cost like 1/10 of a penny each or something, so it's not a disaster. In 270, if you hook these up incorrectly, you can actually cause your function to your circuit to malfunction. Okay, it can actually drag down the outputs on some of your circuits. So it's not just protecting the safety of the LED, it can actually change what your circuit is doing if you forget that resistor. So get in the habit of always putting in that 1K resistor. All right, so that's the output side. So typically we would take our output X here and we would add a 1K resistor and then LED connected to ground. And now whenever it's outputting a logic 1, the LED will be bright, logic 0, it'll be dark. Okay, gotta talk about the input side. So one way to drive these inputs is just take a wire and connect it either to 5 volts or to 0 volts, right? And that's not a bad thing to do. So typically when we build a circuit, we hook power up to these lines on the outside. We might take this red line, connect that to 5 volts. We might take this blue line, connect it to 0 volts. Just so we have power available everywhere. Now if I want to put a logic 1 into this pin, right, I can connect anywhere in that row, and I could just connect this to 5 volts. Now I've got a logic 1 going in. If I want to feed in a logic 0, I could take this and I could connect it to 0 volts. Okay, but that's kind of a pain to do. So what we usually use are these switches. So we get these little switch blocks. And this looks like a chip. It's got 16 legs on the bottom and 2 rows. And each of these little white things will slide. So you can slide it up or you can slide it down. And you have to look at it really closely, but on the side it'll tell you that in this position it's on. There's actually some writing over here on the side that we can't see. So this is on, meaning in this position this pin is connected to that pin. And if you slide it down to where it's off, this pin is disconnected from that pin. Okay, so we'd like to use these, and just like chips we can pop them into our circuit board. And then we'd like to be able to just move these up or down and change whether we're putting a 1 or a 0 into our circuit. We gotta be a little tricky to do that. So this is what our switches look like. We think of it as an arrow that can either be up, that means this side's disconnected from the other side, or if we flip that arrow down, then these two sides are connected. And what we want is that in one position we're putting 0 volts into our circuit, and in the other position we're putting in 5 volts. Okay, we can't just connect this side to 5 volts and say we're done. In this case, if we close this switch, yes, we're putting 5 volts into our circuit. But if we open the switch, we're not feeding anything into that circuit. That's not the same as sending in 0 volts. Okay, so that's the first big, sometimes misconception. Disconnecting the input's not the same as putting it to 0. To put it to 0, we really need to connect this to ground. So here's what we can do. We can take this point of our circuit, put it through a 1K resistor, and pull that up to 5 volts, and then take this side of the switch and connect it to ground. So how is this circuit going to behave? If this switch is open like this, right, this is disconnected, this has nothing to do with the circuit now. Our circuit's going through a resistor to 5 volts, that's a logic 1. But if we close this switch, now this input to the circuit's connected directly to ground, that's a logic 0. This is still 5 volts up here, but we drop 5 volts across the resistor, we got 0 volts here going into the circuit. Okay, this is the one and only way to hook up switches in this course or in Engineering 270. There's about 16 different ways to do it that don't always work. The bummer is sometimes these other ways will work, and then sometimes they won't. It depends what else is going on. So this is the way you want to hook up switches. Okay, and one way to think about it is take your input to your circuit, pull it up to 5 volts, and then add a switch that lets you short it out to ground. Okay, so you can just do it verbatim from that, and eventually it will make sense, or you can think through it, or you can try it out.
Example of that real quick, like with the breadboard, with the protoboard?
Yeah. because I happen to have brought a bunch of stuff with me. All right, so let's take this first input and let's connect it to a switch. And we're going to use this leftmost switch here. So I'm going to assume we've got a power supply. And I'm going to put ground on this blue line on the bottom, and I'm going to put 5 volts on this red line on top. Which means I'm going to take some alligator clips, put them onto these power connections. Now I'm going to take this, plug it into 5 volts on my power supply. I'm going to take this, plug it into 0 volts on my power supply. So those are off somewhere on the lab bench. All right, so this is the thing that's feeding into the circuit. I want to drive pin 1 of this chip. Okay, so I want to take this and I want to pull it up to 5 volts through a resistor. So here's a 1K resistor, and you can't see the colors very well, but it's brown, black, and red. Those are the 3 color bands for 1K. And I can do it as easily as this. Right, just run a resistor from pin 1 through the 1K up to 5 volts. So I've got this part of my circuit now. Let me put the switch over here so we match the diagram. And then I want to take this part of my circuit and I want to optionally pull it down to ground. So I'll put it into this line of the switch up here, and I'll connect the other end to ground. I only grabbed the big wires, unfortunately. And so now one of 2 things will happen. If this is in the open position, my input is not connected to ground, right, because this is disconnected from here. But my input is pulled through a resistor to 5 volts. That's a logic 1. But once I flip this switch and connect this end to here, this point is directly connected to ground, 0 volts. That's a logic 0. That make sense? And you got to be careful which way you put this in, because if this is the on position, then right now this input's connected to ground. This is a logic 0. And when I flip it down, it's a logic 1. But if I flip it over, right, now this is the off position, and so the input's a logic 1. And when I slide it down, that's the on position. This is shorted to ground. So you can build a circuit like this and forget about the chip. Just take a multimeter and measure the voltage right here. And you should see 0 volts, 5 volts.
So, verify, when you said logic 1, is that when the switch is open?
So when the switch is open, that's logic 1. That's going to be 5 volts going to the circuit. And open means like this. When it's closed, which is like this, that's a logic 0. That's 0 volts. But depending on how you orient this, switch open may mean that it's in the down position, or it may mean it's in the up position.
Right. So basically logic 1's at 5 volts going to the circuit.
Correct. Yeah. Logic 1, 5 volts. All right, so with that, we can hook up switches, which means we can send in 1s or 0s by sliding these switches, and we can read the outputs by looking at the LEDs and seeing if they're bright or dark. Okay, that's enough to implement circuits. Which means that our logic diagram, while it's useful because it tells us logically what's going on, right, this is not complete if we want to actually build the physical circuit. We need something more. We need to move from a logic diagram to a wiring diagram. Okay, so let's take a 5-minute break, come back at 1 o'clock, we'll do wiring diagrams, and then we'll talk about debugging, and we'll talk about lab 2. And then we should be done for the day. All right, so here's our logic diagram. We want to turn this into something we can use to actually wire. So we want to make a wiring diagram. Here's the idea of a wiring diagram. Once you complete it, you can hand it to somebody who theoretically knows nothing about Boolean algebra, digital logic, or anything, and they can still build the circuit for you. Okay, it's a blueprint for designing the circuit, for implementing the circuit. Okay, you're designing it, but you're also going to add information on here which says, how do I actually build this on a proto board? So we already talked about switches. So this was our inputs A, B, and C. We want to add some diagrams, some parts to our diagram to capture the fact that we have switches here. So the idea was, take your input, pull it up to 5 volts through a 1 kilo ohm resistor, and then take a switch and use that to ground it out. So we're going to call this switch A. And if the switch is open, this input is logic 1, 5 volts. If the switch is closed, this input is logic 0, 0 volts. Here's another input B. Pull it up to 5 volts through a 1 kilo ohm resistor, add a switch, connect that to ground. That's our input B. And here's our input C, same thing. 1K resistor to 5 volts, optional switch, which shorts out to ground. That's our input C. And again, there's lots of ways you can go wrong. You may be tempted to take 5 volts and one 1K resistor, and then take the other end of the 1K resistor and connect it here and here and here. Because after all, each of these goes through a 1K resistor. They gotta be separate resistors. If you try to use a single 1K and connect all of these together, what you're doing is you're connecting these points to each other. And as soon as I flip one of these switches, all of these inputs will be 0. Okay, there's lots of different ways you can do this, but you've got to make sure that in effect this is what you've got. Okay, each input goes to 5 volts through a 1K and has a switch that can short that input to ground. All right, so we've got switches wired, and as long as this person knows that this little red box with the plastic slides is a switch, and they know where the two sides of it are, they can build this. Okay, we've got 3 inverters here. And those inverters, right, they're a physical device. And the device should say 74LS04 on top of it. And if it does, then we know what the pins on this thing look like. They look like this. And I don't think there's a better picture. Sometimes they show a picture of these like actually inside the chip, but they don't here. But we know, for example, that if we feed an input to pin 1, the inverse of that input appears on pin 2. Or if we feed an input on pin 13, the inverse will appear on pin 12. Because 6A is the input, 6Y is the output of the 6th inverter. And we know there's 6 inverters in here, and we need 3 inverters. So one of these chips has plenty of inverters for us. So we're going to have a section up here in the corner of our diagrams. This is called a component ID block. and it describes each of the chips that we're going to put on our board. And there should be an entry for each chip you put on your board. If you have 5 of these, you should have 5 entries up here, 1 for each. So we're going to have something like 74LS04. And we're going to give it a name, a short name, because putting 74LS04 next to each of these takes a lot of writing. Typically we just call them U something, so we might call this U1. And up here, we also indicate where we connect to ground and where we connect to VCC. I didn't leave enough space. So go back to your truth table and you see ground is connected to pin 7 and VCC is connected to pin 14. And now over here, I'm just going to put a little U1 next to each of these. So that when you say, okay, what is this chip on the proto board? It's U1, oh, that's a 74LS04. And ground's connected to 7, power to 14.
Sorry, I can't see it. Without things down. What did you write under block before?
So this is VCC and
Okay.
ground. All right, well, we also need to know not just that we're using this chip, but which pins we're connecting to. So let's go back to our diagram of this chip, and we've got 6 inverters. We can use any one of them we want for this first inverter. Let's just pick the first one. It goes in on pin 1 and comes out on pin 2. So what I'm going to do over here is I'm going to put a little number next to the input and the output. And this says the input is pin 1, the output is pin 2 of chip U1. We need another inverter for the second part of our circuit. We could go in on pin 3 and come out on pin 4, because that's another inverter. And if we choose to do that, I'll come in on 3 and I'll come out on 4. And we have one more inverter in our diagram, and maybe just to keep things from getting too lopsided on one side of that, maybe I'll come over here on the other side and I'll use pins 8 and 9. And the way these are set up, if I go in on pin 9, I come out on pin 8. Okay, 9 is the input, 8 is the output. So I would label this accordingly. Here's pin 9, here's pin 8. All right, everybody clear with that? That's the essence of all we're doing here. Right, we're just figuring out exactly where we're going to make connections to each of these chips. Now we want a 3-input NAND gate, which is connected to, A, B bar, and C. But if we go to our components on the web page, there's nothing on here for a 3-input AND gate. There's a 3-input NAND, and there's a 4-input AND, and there's a 2-input NAND and 2-input AND, but there's no 3-input AND. So what can we do?
Maybe 2 AND gates.
We can use 2 AND gates. So we want A, B bar, C. Let's take A and B bar and AND those. And then let's take that and AND it with C. And that'll give us A, B bar, C. This thing up here was just A, B bar. So in lab 2, you're coming up with a design for your traffic intersection circuit. And I'm going to ask you to do a wiring diagram. But it says to use only parts that are available on the website. So you can't use a 3-input gate, but you can use 2 2-input gates like this. Okay, well, how do we wire this up? So what's a 2-input AND gate? It's a 74LS08. And they give us a nice little picture here that actually has AND gates in it. So we're going to need another chip. It's going to be a 74LS08. So let's just call that U2. 74 LSOH. Ground is still 7, power is still 14. And now I'm going to label these U2 and U2. We got 4 gates inside this. Question on that? Okay. We got 4 AND gates inside this package. We can pick any 2 that we want. So this first gate over here, we go in on pins 1 and 2 and out on 3. So let's just label our inputs 1 and 2, and we come out on 3. And we need a second AND gate here. We could go in 4 and 5 and come out 6 if we want. So we'll label this 4, 5, and 6. And so on. Okay, so we do the same thing for the second 3-input gate. And that's going to be another pair of 2 input gates. Those can still come from chip U2 because we got 2 gates left in there. And then we need a 2-input OR gate. And we find what the part number is for that. We add that here. We draw the circuit. We list the pins for the input and the output. And then the final output X, we go ahead and we run that through a resistor. And we run it through an LED. And we connect it to ground. And we label that X. And we're done. Okay, that gives you a wiring diagram. And now you can take this diagram, give it to somebody who knows how to read part numbers on chips and count pin numbers and so on, and they can build this for you. And they don't have to know what the circuit does. They don't have to know about this equation. They don't have to know about truth tables. This gives them all the information they need to build the circuit. Okay, that's your goal in a wiring diagram. And if you have a wiring diagram, building this is very straightforward. It's actually a fairly relaxing process if you give yourself enough time, right? You need a U2, you find a U2, you put it on the board somewhere. And you're supposed to connect pin 4 of U1 to pin 2 of U2. Well, you go to U1, you count over to pin 4, put a wire in that hole. You go over to U2, you find pin 2, you put the other end of the wire in that hole, you've drawn this wire. And you just build your circuit up like that. And typically you make a copy of this and you get a highlighter, and each time that you make a connection you can highlight the wire that you've drawn and sort of keep track of things like that, or you can darken it in or whatever. Okay? So here's the golden rule for building circuits in this class. Do not build a circuit until you have a wiring diagram. Okay? If you're given the circuit to already build, like in Lab 2, you can go ahead and build it. But if you're designing your own circuit, don't start putting things on the board until you have a wiring diagram. And chances are, if your circuit doesn't work and you go to a lab assistant and say, can you help me with my circuit? What's the first thing they're going to say? Sure, let me see your wiring diagram. Okay, and if you don't have one, they'll probably say, make a wiring diagram, come back and talk to me then. Because trying to debug this is really, really difficult, right? You've got this bunch of wires and chips and LEDs and resistors, and this is all you know. This is what I wanted to do. Well, what does this wire do? I have no idea. Okay? Oh, I pulled it out. Sorry, where does it go? You have no idea, right? Because you put it in 20 minutes ago while thinking about this. If you've got a wiring diagram, right, it's really, really easy. Okay, so I want to talk, let me talk for like 5 minutes about debugging circuits, which you're not going to need to do for Lab 2, but we're at this point already. So you've got your wiring diagram, you've built your circuit. When you flip your switch, the LED should go on. You flip the switch, the LED does not go on. What do? So you got a few possibilities. What most people do, they rip everything out of the board and they start over. Don't do that, okay? That's not a very effective way to debug a circuit. How many people here have done any programming? Okay, you write your program and you try to compile it or you try to run it and it doesn't work the first time. Do you delete it and start over? Hopefully not. Okay? Same thing, you debug it. You take what you have and you try to analyze it. So let me show you a way to debug a circuit. Okay? Get a multimeter. And most of these have little stands on the back. This one's broken, that's why I got it. You can flip the stand out and put it on the bench and look at it without having to hold it. Okay? Set it to measure voltage, so volts DC. And then take the two leads, and you want to connect a pair of alligator clips to them. Where did my alligator clips go? There they are. All right, so I'm going to use green for ground and red for voltage. So connect a pair of alligator clips. And now take some wire to connect the black lead, which is ground, to the ground point on your circuit. So let's go like this. Okay, so the ground lead of my meter is now permanently connected to ground on my board. Now take the red lead and connect it to the longest wire you can find in your box. Okay, like this. And set your meter to volts, and now you have a test probe. What I can do is I can take this and I can pop it into any hole on my board and immediately see what the voltage of that point is in my circuit. So if I think this should be 5 volts over here, I can pop this into that hole, and if it says 5 volts or something close, I know that everything's good. If it says 0 volts, I know something's wrong. So this is our test probe. Okay, this is how we measure voltages throughout the circuit. So let's suppose a simplified circuit. Let's just suppose the output of this circuit was going through an LED. And the way this is set up, if I flip switch A down and B and C up, the LED is supposed to light up. Okay, so you power it up, you flip the switches, the LED does not light up. That's your final output. Okay, LED is not lit up. What's wrong with my circuit? Time to debug. Okay, first thing to do, this is an LED. If I put 5 volts right here and 0 volts right here, the LED should light up. Take your test probe, measure the voltage on this side. It'll probably say 0 volts. Measure the voltage on this side. Does it say 5 volts? Okay, there's two possibilities. One, it does say 5 volts. There's a problem with your LED. None of this matters. Between here and here, something's going wrong. What could be going wrong? Could be the LED is burned out, could be it's hooked in backwards. So take it out, turn it around, see if it lights up. If not, try another LED. Okay, but you know you got 5 volts here, 0 volts here, any reasonable LED should light up. This is the only place you need to debug now. Okay, on the other hand, you measure this and it's 0 volts. Well, it's supposed to be 5 volts. Okay, well, it should be 5 volts on this end of the resistor. Measure that. If I've got 5 volts there and 0 volts here, something's wrong with that part of my circuit. What's wrong? Well, maybe I had this connected in the wrong hole. Very, very easy to do, right? And that tells you right away, oh, okay, that's the problem. I'll put it over here. Your circuit works, you're done. Or maybe it's not that simple. And when I measure over here, this is still 0 volts. So that was that random wire I pulled out earlier. So let's just put that back in here. All right, so this is supposed to be 5 volts. Well, it's coming out of an AND gate. Okay, first thing to do, measure pin 6 on chip U2. This is why you want a wiring diagram. So whichever one is U2, and you can keep a picture somewhere that shows you this is U1, this is U2, U3, and so on. Count over to pin 6, take a voltage reading right there. If that's 5 volts, you've got a problem between here and here. Check your wires. If this is 0 volts, and we know this is an AND gate, check the two inputs. So measure pin 4, measure pin 5. If those are both 5 volts and the output is 0 volts, something's wrong with your AND gate. Could be a bad chip, could be that it's not actually an AND gate, could be that you forgot to put power or ground on that chip. Okay, so the whole process of debugging is just trying to narrow down your scope to a very small section.
Can you fry an AND gate like you can a
Sure.
LED?
Yeah, if you hook them up backwards, so if you hook chips up backwards, A, they won't work, B, they will start to smell bad, and C, they will get really, really hot. Okay, I don't recommend touching them to see if that's what's going on, because you'll burn yourself. Okay, that was my first experience as a kid with logic gates. They get really hot. So chances are that you'll smell it. Or you can feel close to it, you know, or lick your finger and touch it if no one's looking, and tell it it's hot. But turn off the power, right? Double check your wiring. And if you think that's what's going on, right, you can tentatively sort of feel close to it and usually tell that it's hot. At that point, it's possible the chip's been damaged. But you might just correct your wiring, see if it works. And if it doesn't, if it looks like the AND gate has a problem, just toss it. Right? LEDs, if you hook them up backwards, they just don't light up. It doesn't actually damage them. But these are definitely sensitive. Same thing if you crank the voltage supply way beyond 5 volts, like you put 15 volts into these, it'll probably cook them. So check the voltage setting before you hook them up. All right, so you keep debugging, right? If this input's supposed to be a 1 but it's a 0, right? See where this comes from. Well, it comes from this point in my circuit. Take a reading right there. That's supposed to go through a 1K resistor. Maybe there's something wrong with that, right? Or maybe your switch is closed and you think it's open. If you measure this point and it's 0 volts, but you're pretty sure it's supposed to be 5 volts, and this is 5 volts over here and this is wired correctly, right? Flip your switch. Surprise, it just might do the opposite of what you thought it did, right? That's another really easy situation to be in. So debugging works really, really well, but only if you have this nice wiring information. Okay, so that's the reason for the edict about having a wiring diagram. Okay, we can address all that more when we get to lab 3, where we actually start implementing our circuits. But let's go ahead and look at lab 2. So lab 2 is it's some refresh of what you've done in 120, and it's also some new stuff. So the first 3 experiments are trying to identify an unknown chip. So you'll find either in your parts box or in the cabinet a drawer that says unknown ICs. And they look like regular chips, but they've been whited out on top, so you can't read the numbers on them. Okay, and the goal is to build this circuit and use it to try to figure out what this chip is. So you build your circuit, connect pin 7 to ground, 14 to power. You have an output, which you can hook to an LED, or you can just measure it with a meter. And you have 2 inputs, and the easiest way to drive these inputs is just move the wire to either 5 volts or ground. Okay, we don't have switches that let you do this, that let you move between 2 positions. But just take a wire from pin 1. If you want to feed into 0, connect it to ground. If you want to feed into 1, connect it to 5 volts. And the idea is go through all the possible combinations of 0s and 1s for these 2 inputs. And for each combination, write down whether the output is high or low. So build a truth table for this chip. And once you have a truth table, speculate about what the identity of the chip might be. So go through the data sheets on the website and see which ones have a truth table that match what you got. And then make a hypothesis, this is a such and such gate. Okay, experiment 2, do the same thing but with the unknown chip labeled IC2. And in this case, our inputs are pins 4, 5, the output is pin 6. Okay, develop the truth table, and then identify the component and explain why you think that's what it is. And then experiment 3, use IC3, put your inputs on pins 1 and 3 and your output on pin 4. This one's trickier. All right, and then same thing, figure out from the truth table what kind of chip you think it is. Okay, experiment 4 you've done in 120. This is a refresh on Ohm's law. And this is a case where you really, really want to read the instructions carefully. Okay, so let's just look at part 1. It says measure voltage across the resistor and calculate the current. So you're building a circuit. You've got 5 volts here, you've got ground here, you've got a resistor in between. It wants you to take a voltage measurement between this point and this point, right across the 1K resistor. And then it wants you to use that and your knowledge of Ohm's law to calculate how much current is flowing through the resistor. Okay, your lab write-up, remember, it's got to be a description of everything you did. So you can't just put down, I got 6 volts and 2 milliamps. Okay, you got to have this picture in there. And you've got to have in words somewhere, we built this circuit, we measured the voltage across the resistor. And here's what we measured. 6 milliamps or 6 volts or whatever. Then we calculated the current through the resistor. Show your calculation. V equals IR, V is this, R is this, I is 2 milliamps. All right. Then do the same thing for part B, do the same thing for part C, 2 and 3 resistors. And then part D, you're not building anything, but you're trying to generalize your results. And you're saying, suppose I had 20 resistors. What would be the voltage across each resistor, and what would be the current through the resistors? And you can do this if you think about, n resistors and you apply Ohm's law and you generalize what you did in the first 3 experiments. And what you should end up with is a set of equations. V equals something, probably involving n, and I equals something probably involving n. You can't just say V equals IR and I equals V divided by R. Okay? Those are true statements, but that's not what we're looking for here. We're looking for a formula so that if I say I've got 10 resistors, I can plug 10 into your equation and figure out what the voltage is. And you can check your formula by going back to your first 3 cases. If you plug in n equals 1, you should get the same thing that you got here. If you plug in n equals 2, you should get the same answer you got for B. N equals 3, you should get the same answer you got for C. Okay, so it's a combination of some lab work and some thought exercises. Part 2, exactly the same thing, but with parallel resistors. And here, measure the voltage across the resistors and calculate the current through one of the resistors. Okay, pay attention to the words. Very few people end up doing these the way that they're actually supposed to. I'll get the total current through all the resistors, I'll get the voltage across the resistors, and so on and so forth. So try to stick to what it's asking and ask questions if you're not sure what it's actually asking for. And then same thing, come up with a general formula for n resistors in parallel. What would be the average voltage across the resistors and the current through one of the resistors? Okay, so say the current through here. And then we're back to the traffic control signal system. So in here, you're going to have the sketch of the intersection, which you already did in Lab 1. You're going to have the truth table, which you already did in Lab 1. But you're going to add a design. And it says a logic design. I'd like you to go to a wiring diagram. Okay, so not just a logic diagram, but a wiring diagram, which means I want to see part numbers and pin numbers and switches and LEDs. Okay, everybody clear on that? Okay, so a logic diagram using only the chips listed on the course website. So engrcs.com. And go to resources and component specifications. And these are the things you're allowed to use. All right, and that's experiment 5. And you're not implementing it, you're not building anything yet. Okay, you're coming up with a wiring diagram. The next version of this, you'll actually build it. Okay, but for now, you're just doing a paper design. Yes?
Like the basic system diagram?
I would go ahead and do a system diagram also, yeah. Even though it doesn't say so. Let's always get in the habit of doing a system diagram and truth tables. And I would put your logic equations in there also, right? Again, partially for partial credit, because if your circuit diagram is not right, but I can see the right equations, right, then it means that you were that much closer to the correct solution. That's good for partial
I
credit.
just wanna make sure I don't miss anything.
Mhm.
System diagram, logic equations, truth tables, and the wiring.
Wiring diagram, yeah. And truth table usually comes before the logic equations, because we write it from the truth table.
One last time it was.
Okay, so system diagram, and then the truth table, and then logic equations, and then the wiring diagram with part numbers and pin numbers and switches and LEDs. So 4 basic pieces, and you'll have that for most. If you want to include your logic diagram right on the way to your wiring diagram, you're welcome to do that. But the wiring diagram includes all of the logic usually. All right, so let me talk about these other report requirements. So make sure, and so far I've looked at a few of the labs and people are doing a great job with this. It's awesome. Make sure that you're describing what you're doing in each experiment, right? Don't just jump in and start presenting data or observations, right? What are we trying to do here? Experiment 4. Right, in this experiment, we're working with Ohm's law using a series of circuits, right? Part 1, we build a circuit with 1 resistor in series. Here's a picture of the circuit, right? We measured the voltage across here, and we got this. We calculated the current, and we got that. All right, part B, C. Part D, we developed a formula for voltage and current. Here's the formula, right? That's plenty. Okay, so make sure you have a clear problem statement, what you're trying to do. Identify the theory or process used. I think that's in there also. Document the resulting circuit. Yeah, so that's all what I just said. For the report as a whole, right, so you want a cover sheet. I'm also going to ask you to put an introduction into your lab. Don't just start with experiment 1. It can be 1 or 2 sentences, but tell me what the whole lab report is about. Again, imagine you're at the library and you're pulling down reports and you're looking for a report that works with Ohm's law, right? So you flip it open and it should say introduction, you know, in this lab we did this, that, and the other thing. All right, just kind of what's this report about? And then at the end of the report, I want 3 things. I want a section that talks about lessons learned. Okay, so what did you learn from doing each of these experiments? What's the take-home message here, right? And that kind of goes along with conclusions. Okay, Ohm's law is gibberish. It doesn't work at all. That's a cool conclusion if it's true, right? And you definitely want to publish that if that's what you found. So lessons learned, conclusions. This part C, this is new for 250 versus 120. A new experiment and expected results. Okay, so this trips people up usually, but the goal here is you've got 5 experiments in here. Presumably they have something to do with each other. Okay, well in this one they're all kind of like, you know, further introductory topics, but if you were to add a new experiment, right, what could you have students do that would sort of further expand their understanding, their exposure to this stuff? And you want to spend some time thinking about this, and you want to try to be creative here. Don't take an existing experiment and modify it, okay? Don't say, let's take a 4th unknown IC and try to determine what it is. Okay, yeah, that's a new experiment, but it's kind of like one of the other experiments we already did. Or build a circuit with 4 resistors in series. That's kind of like the other experiment we did. So be creative here, right? Spend some time thinking about it. And the goal of this is to get you to think about why are we doing these experiments, right? Other than you got to do them to get the grade, right? What's the goal here? What are we trying to learn? What are we trying to get practice with?
Can we work on that with their lab partners if you want us to?
You can work on that with lab partners, but I want each person to come up with their own new experiment. So
Oh,
if you
that's
have-
what I was asking. So like we can't, so we all 3 of us can have the same experiment?
No, so it's per person.
Okay.
So if you have a really good idea, don't tell your lab partners. But if you're just kind of kicking around ideas to like start some brainstorming, you're welcome to do that. But yeah, this is per person. And you don't have to do the experiment, okay? But your experiment has to look like these experiments, okay? So you can't just say, build a circuit using 2 chips and see if it works correctly, okay? If I gave that to you as experiment 1, you'd be like, I have no idea what this means, okay? So your description of the experiment should be sufficiently detailed that somebody else could read that description and then do the experiment themselves, okay? So if you want them to build a circuit, tell them what the circuit is. Either give them a circuit diagram or tell them what it's supposed to do and so on, right? So we want lots of detail in here. Does that make sense? So you're welcome while you're thinking about this to bounce ideas off me, right? So I was thinking about something like this for a new experiment. Is that what you're looking for? Right, you can do that. All right, so that's lab 2. Labs are due at noon, okay, beginning of class time. If you thought today's lab was due at midnight, I'm going to let that slide for this time. So, so if you didn't get it in because you were going to turn it in by midnight, that's okay for today. But future labs are due at noon, so I'll probably change it to like 11:59 or something, or 12:01, just so it's unambiguous. All right, questions on the lab? Mm-hmm.
So when we're writing up our lab reports, I mean, in order to describe experiment 3 right there, can we just say we're given this and we were supposed, and we did this? Like, we don't have to painstakingly list each step that we have to go through.
So let's do experiment 1 because that would be the first one, right? So I would say, you know, in this experiment we're trying to identify an unknown chip. We were asked to build the following circuit, picture of the circuit. You can copy and paste from the lab, okay? But good practice, put a little note on there and say, you know, taken from Introduction to Digital Logic or Lab 1 or whatever, right? Just so people don't say that you claim that you drew this yourself. So, you know, we were asked to implement the following circuit. We connected inputs A and B to 0 and 1 and recorded the output and made a truth table. Here's the truth table, right? Based on this, we think that this is a 64-bit CPU, right? That's all you need. And then for experiment 2, you don't really need to sort of repeat all of that. And you could say experiment 2, we did the same thing as experiment 1, but with a different chip and a different circuit. Here's the circuit, here's the truth table, we think this is a such and such.
If we describe our process, do you need pictures of us doing it?
No. You need a circuit diagram almost always, right? So somebody else can build it. But it's a little murky, right? So the understanding is that somebody who cares about this understands digital logic. They understand engineering 250 level logic. They don't know what this lab says, okay, but they know what it means when you say we connected the inputs to 0 and 1 and we made a truth table. So you don't need to say we ran a wire from this pin to a hole that was connected to 5 volts through a power supply, right? So assume people understand the same level of stuff that you understand. It's just the particulars. So the circuit diagram, the truth table you came up with, and so on. And we'll modulate, you know, your level throughout the different labs. If there's not enough detail, I'll let you know. Other questions? All right. Well, we got 10 minutes left, so let's switch gears for a bit. This is our counterpose. This is an interesting course because some of what we do in here will be fairly theoretical. It'll be stuff on paper it'll be stuff with equations and numbers and stuff. And some of what we do in here is, you know, the big circuit board with chips that are getting hot and lights that are turning on and off and so on. Those are sort of different modalities that we work in, right? And we're really kind of moving towards integrating those. So when we work with a circuit on paper, right, we're also kind of at some level working with it in a physical circuit implementation, at least in our head, and vice versa. Okay, so we'll bounce back and forth between those, and that can take some getting used to, but it can be a good thing too. So we're going to bounce back for the last 10 minutes of this class and talk about some almost mathematical aspects of what's going on here. So the subject here is Boolean algebra. And why do we call it Boolean? What does Boolean mean? 1 zeros. Why do we call it Boolean as opposed to the person? Okay, so who is this person? I'll tell you their first name. George Boolean, George Boole. So who is George Boole? I didn't know him, but he studied this stuff that we use today, ands and ors and nands and nots and so on. So when did all this stuff get developed? Ballpark estimate. 1940.
I would say around 1945, actually.
1945. Go back about 90 years. So mid 1800s was when this stuff was being developed. Well before we had a use for it in digital logic, right? But the game at the time was sort of trying to understand how we think in some way, how we logically process information, how we reason. And logic has been around for thousands of years as a subject. And trying to put that on some kind of mathematical footing, that's what was one of the things that was going on in the 1800s. And this system of Boolean algebra is one way to do that, and it turns out to be a way that's really useful when we started developing computers, because computers aren't very sophisticated, right? They don't process information the way we do. So if we can put these things like, if something is true, then do something else, if we can put that on a solid mathematical footing, we have a hope of turning a machine into something that can do something like reasoning and logic. And that's exactly what we've done. So Boolean algebra, so it's ones and zeros, that's also true, right? Or high lows or on offs or trues, false, or whatever. And we've already talked about the different kinds of operations we can do in Boolean algebra. So for example, if we say x equals a dot b, it means that if a and b are both logic 1, then x is a 1, otherwise it's a 0. And we can make truth tables to describe this operation and so on. Okay, well, there's some other aspects to this that we haven't really gone into yet, but they're largely self-evident. For example, if we take A and we AND it with B, we get the same result as if we take B and we AND it with A. That's not really surprising. This is telling us if A and B are both 1. This is telling us if B and A are both 1. Well, that's exactly the same thing. So this doesn't really startle us, right? And similarly, A or B is exactly the same as B or A. And there's a name for that mathematically that's called commutivity. So we can say that ands and ors are commutative. Here's another property of Boolean algebra. Anybody know what this is called? Associativity, excellent. Associativity says if we take B and C and AND those together, take that result and AND with A, we get the same value as if we first AND A with B, take that result and AND it with C. So we can put parentheses around things. And so when we write something like A, B, C, do we really mean this, or do we mean this? Associativity says it doesn't matter, because they're going to give us the same answer. Is that important to us? Are we ever going to use that?
Yeah.
When?
Just now.
Just now. That's exactly what we did when we did this to find a 3-input AND. We said, well, let's AND A and B bar first, and then let's AND the result with C. The reason we can do that and not worry about, oh, maybe we should have done A and C first, is because ANDs are associative. Excellent. So we've got associativity. We've also got distributivity. Distributivity, that's a word. We can distribute, right? A ANDed with a quantity B or C is the same as A and B ORed with A and C. And these things look like elementary algebra operations on purpose, right? This is just multiplying A by B and A by C and adding them together. Right, and it is called Boolean Algebra. It should look somewhat like the algebra that we're used to. And that's sort of by design. Okay, let's try a couple of a different flavor. Suppose I take A and I AND it with 0. Can I say what I'm going to get? Got one vote for A. Got some votes for 0.
A naught.
Got a vote for A naught. Well, what is 0 ANDed with 0? What is 1 ANDed with 0? So this actually turns out to be 0. What about A ANDed with 1?
Is it 1 or 0?
Well, what's 0 ANDed with 1?
0.
And what's 1 ANDed with 1?
1.
So this is A ANDed with 1, and it's exactly equal to A. So that is A. What about A ORed with 0?
A.
That's just A. What about A ORed with 1?
1.
That's a 1. So if we look at this, up here we can replace ANDs with ORs, and everything kind of looks the same, right? Down here, all of a sudden, if we replace ANDs with ORs, things kind of change a little. We've got an A here and an A here, but we've got a 0 here and a 1 here, and our 0 changed into a 1 when we went from an AND to an OR, and something a little weird is happening there. And this gets into the idea of what we call duals. And duals permeate everything we do. They permeate Boolean algebra. You dealt with duals when you did KVL, KCL, because those are dual operations. They come up in politics, they come up in sociology, they govern the universe. And so this is an example of duals, and there's lots of dualisms in Boolean algebra, and we'll touch on some of these starting next time. And it'll take us into something called debugging's theorem, and that's probably where we'll start on Thursday. All right, so I will see you then.